Okay, so in some previous lessons, we've seen that the Fibonacci numbers and the golden ratio sometimes will govern the growth of an organism, like the sunflower, or a whole population, like the bees or the rabbits. All of those had as a governing rule something to do with the Fibonacci numbers or the golden ratio. So now we're going to take a look at two other models, two other rules that can govern growth. So today, the first one we're going to look at is linear growth. Okay, so that is one particular kind of a population growth model. It's a way to describe how a population is growing. And the population could be anything. It could be a population of humans or rabbits or dollars in a bank account. Okay. So we talk about population as a sequence of numbers. So for example, we could write the populations of Greenfield on January 1st for each of the last 20 years, and it would just be a list of numbers, the list of populations. Okay. And we use the same notation that we've been using for sequences for the past couple of weeks. We use a subscript to just denote where in the list you look. All right, so what we're interested in is the transition rule. Okay, a rule or rules that tells you what happens to the population at each transition. So the Fibonacci transition rule was that each number in the sequence is the sum of the previous two. So we're going to look at new kinds of transition rules now. For a linear growth model, this is just one particular kind of growth that we can see. The population always grows or shrinks by the same amount at each transition. Okay. So the sequence that results from linear growth is called an arithmetic sequence, and we learned that name in our first Intro to Sequences lecture. A linear growth model just needs two pieces of info: how much you start with and how much you grow by. How you start and how you grow. So here's a quick example. We have a nuclear reactor, has a 100-ton tank for storing high-level radioactive waste. There are currently 35 tons of waste in the tank, and the reactor generates 5 tons per year. I want to write a recursive and an explicit formula for P sub n, and we're talking about the population of waste in the tank. And then we want to determine how long it will take the tank to fill up. So what we need to know is how much we start with and how it grows. 5 tons a year. So we're starting with 35 tons and we grow by 5 tons a year. So for recursive, that's the kind of formula where you know how much you had the year before. You know the previous number in the list. So if I know the previous number in the list, how do I calculate the next one? You got it. P sub n minus 1, that's the previous number in the list, plus 5. So you just are always adding 5 tons. Each year you add 5 tons. So you take how much you had last year, add 5 tons to it. For the explicit formula, P sub n, I'm going to put down how much I start with. I'm starting with 35, and then I'm going to add 5 over and over again. 5 each year for however many years go by, right? Plus 5n, yeah, because repeatedly adding 5 is multiplication. So I'm going to multiply 5 by how many years have passed. So we start with 35 and we add 5n. So the question was to determine how long it'll take the tank to fill up, right? Which is, we have a 100-ton tank. How long until we have 100 tons of radioactive waste? Which formula do I think is going to be helpful in figuring this out? Explicit, why?
Just do things.
Okay, well, what are you going to do then? Sure, yeah. I could replace P sub n. I want to know how long until the population is 100 tons. So replace the population with a 100. And then we can just solve for n the year that that happens. So subtract 35 from both sides. So I have 65 equals 5n. Divide both sides by 5. And n would be 13. Yes. 13 years, the tank will be full. Now, you don't have to solve it using the explicit method. This is a very algebraic approach. We could also make a list. We could also say n, p sub n, and say, well, right now, we'll call year 0, because no time has passed. It's right now. Okay. We have 35 tons. And each year, we're going to add 5 tons. So we've got 40, 45, 50, 55, 60, 65, 70. Keep doing this. And then we find out how many years it took to get there. So we have 1, 2, 3, 4. 13 years. Yes, we started time at 0. Yeah. Because you measure time in time that has passed. And if there are 35 tons right now, no time has passed. So we call that time 0. So you can solve this either way. And on your test, I believe I'll state the question as, write a recursive or an explicit formula, and you can answer the question either way. You can make a table, figure out how long it takes, or solve an equation. Yes. I believe it's coming up November 20th. Are we going to be able to have a teach? Yes. So the 5 in the above problem, we saw the 5 in both formulas, right? Right here and right here. The 5 is an important part of the transition, right? You add 5 every year. We call that the common difference, which feels a little counterintuitive because you're adding 5 every year. Why would you call it the common difference? And that's because it's the difference between the population sizes in any 2 successive years. So if you go back and look at this table, the difference between any 2 successive years, 45 minus 40 is 5, 50 minus 45 is 5. So we call it the common difference. In some cases, I can give you different starting information. In this case, I gave you P3 and P6. And I want you to try to find a recursive and an explicit formula for Pn. So work in your groups, see what you can come up with. Okay, I saw lots of different approaches here. I'll show you a couple that I thought explain what's happening nicely. So I saw some people do this and make a table and say we have 0, 1, 2, 3, 4, 5, 6, and put in the ones that they know, right? P3 is 28 and P6 is 40. Okay. And then we said, okay, well, how much do you add to 28 to get to 40? 12. And how many spots did I go? 3. So take that 28 and divide by 3 and you get plus 4. Right? And yeah, take the 12, divide by the 3 spots. So if you go 4 each spot, you should land at 40. So 28 plus 4 is 32. 32 plus 4 is 36. And 36 plus 4 is 40. So we now know the transition rule is plus 4. So to go backwards in the list, we can subtract 4. 28 minus 4 is 24. Minus 4 is 20. Minus 4 is 16. So then to write my recursive rule, I can just say, well, the population at any given year is equal to the population from the previous year, which is p sub n minus 1 plus 4. And then for my explicit formula, population in any given year, you can say, well, I'm going to start with my initial population of 16, and then I add 4 over and over again, and adding 4 over and over is multiplication. So you would do times 4n plus 4n. Any questions on that one? Okay. All right, so you don't need to memorize these because we just answered a question without knowing any formulas whatsoever, right? But these are the general formulas for linear growth. We have recursive. You have to state up front what you start with, and then you give a rule of how it grows, where you do Pn is Pn minus 1 times the common difference. And then for explicit, we give the starting amount, then we add the common difference n times. So no need to memorize this. We just came up with 2 formulas without ever knowing the general formula. We came up with 2 equations without knowing these. But if you're a formula person, you know, write them on your sheet for the test and refer to it. Okay, so I want you to work on this one in your groups now. Manufacturer currently has 387 widgets. He's trying to ramp up his inventory. He's going to increase his inventory by 37 widgets per week. See if you can answer these questions. Okay, so how many widgets will the manufacturer have on hand after 20 weeks? 1,127. Can you tell me how you got that? Right, because we're going to add 37 a week for 20 weeks. And then add the previous inventory. So this would come out to 740. And then you take your previous inventory, 387, and add 740. And that comes out to, say it again, 1,127 widgets. Good. So what you did here can help inform writing a formula. Okay. So you can say, you figure out how much you add to the inventory by taking 37 times the number of weeks, and then add to your current inventory. So if I want to write an explicit formula, I would say P sub n, my population of widgets after n weeks, is 387 that I started with, plus 37 a week for n weeks. So when repeatedly adding 37 is a multiplication. And then for recursive, we would just say P sub n, the population of widgets after n weeks, is P sub n minus 1, the population from the previous week, plus 37. Good. And then how long until the manufacturer has 720 widgets? Anybody get this one? How'd you come up with it? Okay, so you're saying if I subtract the original amount, that comes out to 333. Okay, thank you. And you're saying this is how many I have to make, right, to get to 720? Need to make this many. And I can make 37 a week. So you say to figure out how many weeks it'll take, I take my 333, divide by 37, and you get 9 weeks. Okay. So that's sort of a logical think it through method of solving this. One of the great things about algebra is that it gives you sort of an automatic tool to use to solve a problem like this that you can do without actually even understanding what you're doing, right? So if I start with my explicit formula, P sub n equals 387 plus 37n, the number they gave me, 720, is that the population of widgets or the number of weeks? It's number of widgets. So I'm going to replace the P with the 720. And then I would solve this thing for n. And the first thing I would do was do 720 minus 387, which is the first thing I did up here when I was just thinking it through logically, right? So 720 minus 387 gives me 333. And then I would divide both sides by 37, which is the second step I did up here when I was just trying to think it through logically. And we end up with n equals 9. So you can do it either way. You know, if the algebra is something that's comfortable for you, do it with algebra. If you'd rather just sort of think about what's happening, do it that way. Or you could make a table. That takes too long. Okay, so this is just sort of a summary. In a linear growth model, you add the same amount at each transition, and the sequence that results is called an arithmetic sequence. So let's think about this widget manufacturer again. He's trying to build up his inventory, right? He's not going to put all these widgets on the market at once. He's building it up to save them. Maybe he's anticipating a big demand 2 years from now, so he's going to store them all and release them into the market at once. So let's say it costs $10 per week to store a widget, and he plans to store all of his widgets for the next 2 years. How much is he going to spend on storage?
Are we storing one widget at a time for $10 a week? Or is it all widgets?
Each widget costs $10 a week to store. Each widget costs $10 a week to store. So he has 387 that he's going to have to store for 2 years, right? So 387 times $10 a week, right? Times 2 years, which is 104 weeks. So for those 387, $402,480. He's going to have to. Yeah. So now, discuss in your groups. This is how much he has to spend on storage for the original 387. Then he's going to add 37 widgets a week to his inventory. And he has to pay another $10 per week for those, but they're not all being stored for 104 weeks. Does that make sense? They're being stored for fewer and fewer weeks.
How do you do that?
No.
How do you do that, though?
Take a few minutes and think about it. Okay, so I've had several people start to think this through, and some people are saying, okay, well, next week I'm going to produce 37 widgets. I have to spend $10 a week to store them for how many weeks? 103. 103. Because it took a week to produce them, so they didn't need to be in storage for that week. So that is going to come out to $38,110. Okay. And then the next week after that, I'm going to produce 37 more times $10 a week for each one times 102 weeks. Because it took 2 weeks to get these made, so I only have to store them 37,740. Good. And then I'm going to keep doing this, right? I'm going to do 37 times 10 times 101. 37,370. Okay, and so I kind of know how to figure out what the cost is for each set of widgets that I produce, but I do not want to I don't want to calculate 104 numbers and write them all down and then add them all in my calculator. Like, that's just such a huge pain. So what's the last number I'm going to put in here? Times 1 week, which would be 370. And then that's the last number I have to add, right? Okay. And so how many of these calculations are there? 103, right? I went down to 1, starting at 1 and go up to 103. Okay. So somebody said do what we did before. What did we do before? Yeah. Yeah, so back when we talked about pairwise comparisons in the voting, we talked about the number of pairwise comparisons. We had to add a long list of numbers, and we did this little trick. So let's see, my long list of numbers is going to be 370 plus blah, 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 plus, and then my last numbers are 37,370, 37,370 plus 37,740, 37,740 plus 38,110. And this has to add up to some amount that we don't know, right? And that amount should be the same if I write the sum backwards. So if I start with 38,110 plus blah, 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 blah.
So you add 38,110 plus 370?
Yep. Now, how much are these changing by? What's my common difference in these values? 370. Yep. So 370. So 370 plus 370, what's that? 740. Plus another 370, what's that? Yep, 11110. There we go. So that should add up to the same amount, right? Whether you add forwards or backwards, order doesn't matter when you add. So what I do is I add these two equations together. 370 plus 38,110.
Should this go into the remainder part or number 10 or 12?
38,480. And you'll notice if you do all of these additions, they'll give you 38,480 each time. It is. And that's going to equal 2x. X plus x is 2x. So I have 38,480. How many of them do I have? How many am I adding together? 103, right? Because that's exactly why I asked you over here. How many numbers am I calculating here? It was 103 calculations. So I'm doing 38,480 added to itself 103 times. So it's multiplication. So times 103 and divided by 2, and I get x is 1,981,720 plus the initial. So that's how much for the widgets that we are creating each week. Plus we have to add this 402,000 for our original 387 widgets. So plus 402,480 is 2,384,000 total cost. 2,384,200. So this is cost to store the widgets we're producing. Being produced over the 2 years. And then we had to add to that the cost to store the original 387 widgets that we had. So holding on to inventory is a very expensive prospect, right? And manufacturers generally don't like to do it, right? They don't like to hold on to inventory because it's expensive. They would rather put it out in the market and sell it and make money off of it than pay money to store it and make no money off of it. So, but sometimes it is profitable to hold on to your widgets if you anticipate a shortage will happen later and you can charge a large amount for your widgets. Right, yeah.
Not for sale side.
Or diamonds, right? Diamonds are another thing where there's actually like tons and tons of diamonds in the world. They're not that rare, but the diamond industry only releases so many into the market so that they can keep the price really high. So the arithmetic sum formula, which is, you don't have to know the formula. You can always do this little trick that we just did where you write it out forwards and backwards. But the general formula, and I'm not going to write it in symbols. I'm going to give it to you in words because I think it's a little clearer. You want to add a long list of numbers that happen to form an arithmetic sequence. So that is, to get from one number to the next, you're always adding the same amount. Okay. To get the sum, you just add the first term and the last term, multiply by the number of terms, and then divide by 2. So in my sum, it was 370 plus blah, 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 plus the last number was 38,110. I could do it quickly using the formula where I add the first and the last term. So 370 plus 38,110. Multiply by the number of terms, which was 103. And then divide by 2. And you get the sum. So this is equal to 370 plus 38,110 times 103, the number of terms, divided by 2. Okay, so I'm going to have you try one. Remember the nuclear reactor, currently storing 35 tons of waste and producing 5 tons per year? Well, the town in which that reactor is located decides they're going to start charging a tax on that nuclear reactor, the company that owns it. And each year, the town is going to charge the reactor $1,000 for each ton of waste that it is holding in storage. So assuming the tank isn't ever emptied, how much is the reactor going to pay the town over the next 5 years? Starting this year. Okay, so this year, how much is the town going to be charged in taxes this year? $35,000, right? Because they have 35 tons of waste in the storage tank. They're going to be charged $35,000. Next year, we'll call this year 2, I guess. Okay.
Wait, is that year 10? Don't you want to start on 0 though?
It doesn't matter, as long as you do a total of 5 years. You can call this year 1 or year 0. If you call this year 0, you're going to go 1, 2, 3, 4 to get a total of 5 years.
Oh, okay.
Yeah. So in the next year, they're going to be charged $45,000, and then $50,000, and then $55,000. So that's a total of 5 years of taxes starting this year. So I just need to add these numbers up. I need to find the sum of these. And since there's only 5 of them, you could just type them in your calculator and add them up. Or just for practice, we could do our little formula where you add the first and the last. So we'll do 35,000 plus 55,000. Multiply by the number of terms I'm adding. How many numbers are in this list? 5. And then divide by 2. And you get 225,000. So over the course of 5 years, the town's going to make $225,000 in taxes from this nuclear reactor. Okay, so I have a little activity for you to work on in your groups. And I actually researched these numbers, and I'm not saying that they're guaranteed right, but I did try to look them up. And I want you to think about oil production.